Welcome back, everybody.
Welcome back, everybody.
Welcome back. So, tell whether the table shows linear, exponential, or neither. I guess it could show neither, right? We will end up finding whether something is quadratic or not later on down the line. So I guess it could be neither for right now if it turned out quadratic. What do you look for if it's exponential? What do you look for if it's exponential? Multiplication, right? Multiplication. Do I have that in this first one? What do you see? What is the pattern that you see? Ravel? Division. Isn't division the same thing as multiplication by a decimal, though? You see dividing by 2, right? Isn't that the same thing as times 1/2? Yeah. So is this exponential? Yes, this is exponential. If we wanted to go so far as to write out the equation, I didn't ask you to, but if you wanted to, you would put starting value times 1/2 to the x, and there's our exponential function. Take a look at number 2. Is that exponential? Is that exponential? No. What pattern do you see? Yeah, -1. That's just linear. Make sense? Questions about that? All right, let's get to our homework. Let's go over some of the questions. I definitely want to go over one of the graphing ones. People, stop putting question marks on your homeworks. Stop doing it. Try something. Don't just put a question mark. Try something. Guess what? We do a problem like every single homework problem within our notes daily, right? Did we do problems like 1, 3, and 5 in our notes? Yeah. Did we do problems like 7, 9 in our notes? Yeah. Did we do problems like 11, 13, and 15 in our notes? Yeah. Did we graph in our notes? Yeah. Stop putting question marks. Stop doing it. Go back to your guided notes and copy exactly what we did. Stop putting question marks. Okay? All right, so what questions do we have then? Maddie? 21. So let's take a look at that graphing one. I'm glad we're going to do at least one graphing one. Now, how did we graph in our guided notes yesterday? All we did was just do -2, -1, 0, 1, 2, right? That's all we did. So that's all I'm going to do now. Let me get rid of the evens here. So let me just make a table of values. X, Y, -2, -1, 0, 1, and 2. So let's go and plug it in. We've got 0.5 times 8 to the, and then we got -2. -0.008. Negative? No, positive. 0.008. And then we have -1. Same thing. 0.0625. And then we've got 0. Should be 1/2. 0.5. We've got 1. And then we've got 2. 32. Okay, so there are my coordinates. Now I have to create, what's wrong? Uh-oh.
You have something different on the example. Like on here. It says
For real? Uh-oh.
Oh, wait. What?
for like the first one.
Oh, that's weird. Did I do that one wrong? Up on the board? Or did I do it making my notes? 0.5 times 8 to the -2. Oh, that's weird. I must have done it wrong on the paper. Yeah, I said 0.031. That's weird. The rest of them are right, though, right? Yeah. Ooh, it's funky. Now, at any rate, it's almost negligible because it's just a really small number, right? Will the graph have the same shape and look? Yeah. So let's take a look at how it's going to be. Now, do I have to make a symmetric graph every single time for these exponentials? No. We don't need a 10 by 10 graph, right? I see a lot of people do this graph on your notes or on your homeworks. No, you don't need it lined up in the center. No. The reason being, is it ever going to cross the x-axis? No, that's the idea of an asymptote. If it's above the x-axis, it's going to stay above the x-axis. If it's below the x-axis, it's going to stay below the x-axis. This one stays above. So we're going to say -1, -2, +1, +2. And then it looks like I go all the way up to 32. Okay. But really small to start out with, right? Let's go by fives, I guess. 5, 10, 15, 20, 25, 30, somewhere up there. Okay. So now we have -2, comma 0.008. It's like right there. -1, comma 0.0625. Okay, like right there again, right? Should just be a little slightly above it. 0, comma 0.5. Okay, still down there. 1, comma 4. 2, comma 32. And there's my graph. Key things that I'm going to look for here. I want to see the curve. I don't want to see a straight line. I want to see a curve. I want to see the coordinates that you plotted. And I want to make sure that it does not cross the x-axis, because that's that idea of an asymptote. Questions there? What else would we like to see? Yeah. 17, same type of thing, right? So I'm just going to erase this and redo this problem. So 17 is -4 to the x. So -4 to the negative. Whoa, no, to the, not parentheses, to the -2. And that gives me -0.0625. That's not a pen. And then we have -1, which is -0.25. And then we have 0, which is -1. And then we have, oops, that's a 5. We have 1, which is -4. And then we have 2. Come on, buddy. Come back to me. Which is -16. All right, now I need to change my graph, right? Is this above the x-axis any longer? No, this is below, and it's going to stay below. So now I'm going to redo my graph, but I'm going to put the axis up here. Okay, I've got to go -2 to 2, so -2, -1, 1, 2. I've got to go all the way down to -16. So maybe we'll do by twos. -2, 4, 6, 8, 10, 12, 14, 16, 18, 20. -20. Put that down there. All right. So we have -2, comma -0.0625. So -1, comma -0.25. Okay, a little bit lower. 0, comma -1. Okay, right there. 1, comma -4. Oh, no. Sorry, I was going by twos, wasn't I? So right there. 1, comma -4, which is right here. And then 2, comma -16. 2, 4, 6, 8, 10, 12, 14, 16. Somewhere around right there. Yeah, no. It almost looks like it bounces back down. It shouldn't. Should correct that. I should hit that point too. Smooth curve. Arrow on the end. Make sense? All right, let's get to the notes for today, shall we? Okay, yesterday we learned the basics about exponential functions. Today we learned the application. Remember me showing that like the bacteria video? That is what's called exponential growth. And you can model that growth with an exponential growth formula, which is what we will learn today. There are two formulas that you will need to use on your test next week that you will need to memorize that we will learn today. It is the exponential growth formula and the exponential decay formula.
You still have it.
Yes, sure. All right, so by definition, think about the terms exponential growth. Exponential, meaning something's happening very fastly. Whether it's growth or decay, the word exponential really means something's going to happen very rapidly. And if it's exponential growth, it's just going to mean it's going to get bigger very, very rapidly. Exponential growth occurs when a quantity increases by the same rate. Now, please pay attention. It is not by the same difference. I'm not constantly adding. I am growing by a certain rate, right? I'm growing by a certain rate. That rate is basically your percentage of growth, okay? Your percentage growth. So maybe I'm growing by 18%, or maybe I'm growing by 50%, or maybe I'm growing bigger than that. When this happens, the value of the quantity at any given time can be calculated as a function of the rate and the original amount. Please box, highlight, circle, do whatever you need to do to that formula. That is the exponential growth formula. You will need to memorize that for your test on Wednesday. That is the exponential growth formula. Now, thinking back to yesterday, can anybody remember what was the number that was always outside the parentheses? What did I keep calling that? The number outside the parentheses. What did I keep calling that? Like we had in one of these examples. Okay, so 4. What did I keep calling 4? The starting value, right? The base number, he said. The starting value, right? That starting value. Right? We kept calling it that starting value. And I said, if you know your starting value, that's the number that goes outside the parentheses. That's the same thing here. Your initial amount still goes outside the parentheses. And what was the number inside? That was the amount I was continually doing what? I was continually multiplying by, right? That was my rate of increase. Same thing. The rate of increase goes inside here, but now you just write it as a decimal. So if I'm going 18%, if I'm growing 18%, my R value in this case is 0.18. If I'm growing 25%, my R value is 0.25. If I'm growing at a rate of 30%, my R value is 0.3. And then take a look, it's raised to the T power. Now X power. And that X power is usually time. That X power is usually time. So if I'm growing exponentially at a rate over the course of 10 days, 10 is our exponent. Okay, so let's practice it a little bit. The original value of a painting is $9,000 and the value is increasing 7% per year. Write an exponential growth function to model the situation, then find the painting's value in 15 years. Now, by the end of our lessons, I should not need to give you that sentence. Like on your state test, they don't tell you when to write a linear function versus an exponential function. What about that context should tell you that it's exponential? Without being told explicitly that it's exponential, what about that context is telling you that this should be an exponential function rather than a linear function? Mason?
There's an original value, and it keeps growing.
How? How does it keep growing? By a
percent.
Exactly. And that's what tells you it's an exponential rather than a linear. Percent increase, right? Percent growth. That is exponential. Okay? So let's write it out. The exponential growth formula is A times 1 plus R to the X. A times 1 plus R to the X. On your test on Wednesday, I will say, okay, give me the function. What stays in when you give me the function? X. x should stay in there when you give me the equation, because it's like saying y equals this thing, right? Or f of x equals this thing. Okay, so let's write it out. Y equals, what's a in this case? That 9,000, the original amount, 9,000 times 1, standard 1, plus, what's r? Brandon? Okay, as a decimal, 0.07. And then raised to the x. Yeah.
Is the X 15?
Yes, but if I say write the equation, like write the exponential growth function, this is the function. Now, I'm only going to do one thing to simplify it down. I'm just going to make that 1 plus 0.07, 1.07. Because that's really what an exponential function looks like, right? Original amount times base to the power. Okay, it says then find the value of the painting in 15 years. And Zach correctly pointed out, okay, that means I take 9,000 times 1.07 to the 15. So let's see. Okay, this painting started out at $9,000. Over the course of 15 years, I'm only growing at a rate of 7%, right? And remember the thing being raised to the exponent, that's really going to tell you how rapidly something's going to grow. So it's great that this costs a lot of money. But let's see. Over the course of 15 years, wow, I guess it did grow a lot. It's almost tripled in value. 24,831. Let's go to the nearest whole dollar. 24,831. A lot of investments grow exponentially, or hopefully not, but decay exponentially. Okay, things like that happen. Growing exponentially or decaying exponentially. A sculpture is increasing at a value at a rate of 8%. And its value in 2018 was $1,200. Again, right there, I can stop, and you should know that this is exponential growth. Okay, we have our rates, we have our time, we have our original amount, right? So we have our y is equal to a times 1 plus r to the tx. Okay, let's write our equation. What's our a in this case? What's our a? $1,200. 1 plus, okay, what's r? Brandon? No, it's the pirate's favorite letter. R. Just kidding. 0.08. You were right. 0.08. I was trying to make a joke. Yeah, I scared you. Yes. It's the pirate's favorite letter. R. I'm a scary guy.
This chair keeps just like depositing sand over the
Depositing. Why do these chairs do that? Don't make it happen more.
How did it
It's like sawdust. It's sawdust from them like making it talk. Okay. Now it says find the value in 2024. Okay, what's my exponent? What's gonna be my exponent, Zach? 6. Because it was 2018 and now it's 2024, so 6. Oops. 6. 1,200 times 1.08 to the 6th. Which is going to get me 1904.25, or in nearest whole value, 1904.
This is pretty easy. But I mean, I know you're gonna mess it up somehow.
No.
Easy.
Honestly, that is very, those are the types of questions that you get on your state test. But they don't explicitly tell you to write it as exponential growth. They'll just be within all of the other questions, and you have to recognize based on the situation, okay, I'm growing, so I know I have to use exponential growth. And if it's by 1%, that tells me it's exponential. Yeah.
Why do you put 2 Y's in the dollar sign?
Did we have this conversation?
Yes.
I did the same thing.
Because that's what you do.
No, it's supposed to be 1.
Okay, So what happens if something's exponentially decaying? What's up?
I was gonna ask you about
Oh yeah, go ahead. What happens if we're exponential decaying? Well, it occurs when a quantity is decreasing, right? Decay means to decrease by the rate each time period. Just like exponential growth, the value of the quantity at any given time can be modeled by this situation. Go ahead and box, circle, do whatever you need to do to this equation. But the thing is, if you memorize the exponential growth formula, you've basically already memorized the exponential decay formula. What is the only difference between growth and decay formula? What's the only difference, Maddie? Yeah, you subtract instead of add. You are subtracting from one rather than adding from one. Now that's a really interesting point because in an exponential growth, my base is going to be bigger than 1, right? So I'm continually multiplying by a number greater than 1. So it's only going to make things get bigger and bigger and bigger. If I subtract from 1, that's going to be a number less than 1. Oh, that means that's like a 1/2 to the certain power. Is it going to get bigger? No, it's going to get smaller. Think about multiplying by 1/2. If I start with 10, or if I start with 30, I go 30, down to 15, down to 7.5, down to 3 point something, down to 1 point something, and so on and so on and so on, right? If I keep multiplying by 1/2. So that if the base is a decimal less than 1, it's going to decay instead of grow. It's going to decay instead of grow. Notice an important difference between the exponential growth functions and exponential decay functions. For exponential growth, the value inside the parentheses will be greater than 1. For exponential decay, the value inside the parentheses will be less than 1. The population of a town is decreasing at a rate of 3% per year. In 2020, there were 1,700 people. Write an exponential decay function to model the situation and find the population in 2023. So we can use exponential growth and decay functions to model situations that might tell us about the future. All right, so starting value, again, the equation of y is equal to a times 1 minus r to the x. How do I know to use the minus instead of the plus? The word decrease, right? Look at the context. Is it going up or coming down? If it's going up, you use a plus. If it's going down, you use a minus. Okay, what's our a value in this case? What's our a value here? Chloe? 1,700. And then we have a 1 minus what? Robert? 0.03. Well, I said 2023. I meant 2032. 2030. And I got to raise that to the x. Okay, so the only thing that I'm going to change here is I'm going to say y is equal to 1,700. And then I'm going to actually perform that 1 minus 0.03, which is 0.97 to the x. Okay, so there's our exponential decay formula. So you don't see the minus when you're all done with the equation, but you notice that it's less than 1. All right, and now we want to figure out, well, what's my power going to be then? When I go to calculate 2032, what's my power going to be, Chloe? 12. Good, 12. So I have 1,700 times 0.97 to the 12th power. So over the course of 12 years, my population is going to grow. And let's round it to the nearest whole person, 1,180. One big thing to check real quick right at the end. Okay, I said my population was going to decrease. Did it actually decrease? Check that. Make sure it does. Okay. Let's take a look at one more of those. The fish population in a local stream is decreasing at a rate of 2.5% per year. The original population was 48,000. Again, right there I can stop and say, I know this is exponential decay. I don't need that next sentence to tell me that. Y is equal to a times 1 minus r to the x. All right, so what is my a value again in this case? What's my a value, Izzy? 48,000. 1, and again, I'm using the minus. What's R? What's R? That?
2.5.
Ooh, come on. 0.025.
Yeah.
Yeah? Watch out for that.
I was about to say it. You already said it.
1 minus 0.025 is 0.975. So y is equal to 48,000. 0.975 to the x. Again, perform that operation in there to get you the equation. All right, then it says find the population after 7 years. Okay, so 48,000 times 0.975 raised to the 7th power. So after 7 years, it should decrease down to, and we'll go to the nearest whole value, 40,204. Fish. Questions about that? Now, that is all the stuff that we would probably be asked on the state test. The next thing that I'm going to show you is this thing that's called compound interest. It doesn't come up a lot. It used to come up a lot on the state test, but Ms. Napoltz and I were talking. We haven't seen it in like 5 years or so come up on the state test. We used to like drill this because it was coming up all the time. We have not seen compound interest come up. Whoops. Oh, are these on your paper? Oh man, I'm not even there yet. Whoops, sorry. I'm skipping an example here. Oh, sorry. Rewind. Determine whether the function shows exponential growth or exponential decay. Pretty easy for the tables. Is it going up? Is it coming down? Exponential growth or decay? Exponential growth or decay? Growth. How do you tell based off the look of the equation whether it's exponential growth or decay? Elijah? Or less than 1, right? So, Elijah, tell me, growth or decay? Yeah. Because this is 1.07. Because it's just a little bigger than 1, it's going to be growth. What's the percent growth? How much is this growing? Mason? How much is this growing? Elijah? Oh, be careful. Just take off the 100. Just 7. Yeah. Just 7% growth. 7% growth. Yeah. And how much did I start with? 5. I know that. Okay, this next one, what's that going to be then? Decay. Now that one's a little harder. What's the percent decay? Rainer? Yeah, good. 2%. 2%. Because it's 1 minus 0.02 gives us 0.98. You got to figure out the number that we subtracted away from 1 to get the percent growth or percent decay. Yeah.
We have to tell you why I guess decay or growth on the test or anything.
You should be able to back that up. Yeah, if you need it. You know what? I'm not going to worry about this. I'm not going to worry about the last example. I'm not going to teach compound interest. There is one homework problem tonight that deals with compound interest. You can just bypass that. It will not affect your grade at all. Yeah. If I think about, you know what? I can't, since it's already given to you guys. I can't change it. This is the online assignment. This one is an online assignment. You go to the Big Ideas website. And it should be there, should be already given to you. You two have not done one of these yet, have you? Come here real quick.